Hello, welcome back to another RATS Technical Sessions webinar. This will be our 10th one so far. I'll make my announcements pretty brief. For the local Alberta people, just want to mention we are not going to pursue a golf tournament, sadly, for 2021. That's our bad news. We have a couple of things of good news though. One is that we have our 6 recipients identified now for our scholarships, and there they are on the screen. I don't know if I can pause that. And anyways, Red Deer College, Nate, U of A, we have Trevor Newfield, Dexter Tatry, they're identified earlier on, and I'm not sure if I want to try and pronounce these names. Oladoyan Solomon, Ty Halber from Nate, Alexander Samuel from U of A, and Ali Vajili. So congratulations to them. We'll have more going through through our various organizations or institutions later on. So I'll hand it over to Ralph now, and we'll carry on.
Yeah, thank you, Andrew. Yeah, I'd like to welcome everyone to our RATS technical session, and we aim to make these all interesting and informative. And I do have a little bit longer announcements than usual. So just a reminder, your microphones are muted, but we will have some questions coming up, and we'd like to get your responses. Well, we'll have both polls and questions. The questions, some of them are going to be answered through the chat function. So if you go to your control panel, you'll see there's a place where you can click on the chat button and enter your answer there. The presentation, as always, is recorded, and you can access it on our website afterwards. There is additionally some handouts. They are PDF files, and they are again accessible through the control panel for this GoToWebinar. We'll have a survey at the end of the presentation after it's all done, just to get your feedback on how everything went and suggestions for the future. We do have some interesting seminars or webinars coming up. I'd really like to mention next month, exactly 1 month from now, we will have a webinar on the API, American Petroleum Institute 610 standard, the 12th edition, which has just recently been issued. So this presentation will be going through what changes happened in the standard for centrifugal pumps. That will be very interesting. And we have a speaker who was on the 12th edition committee from Clyde Union. The following month, we have a presentation from Rotating Machinery Services, and the topic planned to be on power turbines. And we have another one coming up on VFDs the month afterwards. So these will continue to be presented for your education and entertainment. So I think that was all that I needed to mention at this point in time, and I'll turn over the presentation to April Cook from Burkhart, our guest speakers today.
Okay, thank you very much, Ralph and Andrew. I'll just let David get our presentation slides up there. So I'm really excited to be here today. Thanks for having me. So good afternoon, everyone. Thank you for joining us today to talk about dry running sealing materials and reciprocating compressors. For those of you who don't know me, I'm April Cook, and I'm the Alberta Sales Manager for Burkhart Compression. We are a compressor OEM with 175 years of experience. I've been with Burkhart now for 7 months, and I'm based out of the Edmonton office. I've been in the oil and gas industry for 10 years, and I've spent most of that time in the compression industry. For the last 7 years before starting with Burkhart, my career was focused on natural gas compression, and I spent the majority of my time on the road visiting customers at gas plants and compressor stations in the field. Burkhart Compression is proud to be a sponsor of the RATS Rotating and Turbomachinery Society, and I have 2 very experienced colleagues with me today to help present. We have David Flood, who has been with Burkhart for over 6 years, and he is based out of the UK. He spent 19 years at Morganite in the Graflon division, which was purchased by Horbiger. He also spent 7 years representing Layard, which is part of France Compressor Products and is now known as CPI Compression. I also have with me here today Craig Bowern, who is located in Ontario, Canada. Craig has been involved with Burkhart Compression since 2006, and Craig is a millwright by trade and was a former reciprocating compressor specialist, servicing Burkhart compressors locally or globally. Craig has been in his current management role since 2013. Sorry, I'm kind of minimizing you there, Craig. So we can move over to the agenda slide.
Oh, there we go.
Okay, thanks, David. So as I mentioned, our topic is dry running sealing materials and reciprocating compressors. Like Ralph said, we do have a chat function, and this is an interactive presentation. So please feel free to add questions as we go along, and we will have time for questions and answers at the end of the presentation. If anything triggers a question about your reciprocating compressor that does not pertain to today's topic, feel free to reach out to us after the presentation and we can set up a meeting or a phone call to discuss. And I would like to emphasize that we can help with all brands of reciprocating compressors, not just Burkhart compressors. So please keep that in mind during and after the presentation. So today we will touch on the different ways that compressor pistons are sealed, the challenges faced, the failure modes, methods of diagnosis, and some solutions developed to increase the reliability of reciprocating compressors. We will explore new material technologies and the advantages they provide. So without further ado, I will pass the floor on to David Flood.
Thank you very much, April, for that wonderful welcome. So we're going to start, I'm going to start by asking you a question, which is part of our poll. And it's, why is this ring worn so much? And you've got a choice of 5 options there that you can select, and I'm hoping Andrew is going to bring the poll up, and we will give you a few minutes or a few seconds to answer the poll.
Yeah, I'll give them a brief moment just to really study the pictures closely to see what they can identify to that, and then I'll run the poll right after that.
There also might be more than one correct answer.
Yeah.
Oh, well, in that case, I have not set up the poll to have multiple answers.
That's all right.
Take the best.
We'll take the percentage.
Okay, so here we go. You guys can have your input, and we'll show you the answers later on in the presentation. I apologize for not giving you more than one option.
That's right. I can't see what you see, so.
Okay, what I see is more than 3/4 of people have responded, so I'm going to close this down in the next couple seconds if I don't see anything else.
Okay.
Okay.
Right.
So that is done. We'll come back to that later.
Right, and I also actually have another question to ask. So we have a packing case here. It's as it came out of the compressor. And if you'd like to make a comment about what you see or what you think, you can make that in the chat, and we can maybe see what people think as they go through. We'll revisit this picture a bit later on in the presentation. So we mentioned that we were going to talk about the different sealing systems of reciprocating compressors. So within Burkhart, we manufacture a wide range of machines. So in this case, the one pictured is a hyper compressor. So that's 50,000 PSI. So you get an awful lot of pressure, compressing ethylene to make LDPE products. And here, for instance, we just use a plunger. So there are no piston rings sealing it. It's just a plunger, a very close fit between the plunger and the cylinder. And then we have some packing rings to then seal from the crankcase and the low pressure oil systems and some other things. So you can see here the parts, and this plunger, for instance, on the second stage of these compressors, it's made of solid tungsten carbide. That surface is extremely smooth. We'll touch on surface finish again later on, but these are very smooth, simply to prevent crack propagation. You can see here where the actual cylinder area, this area is where the valve goes, and then we have bronze packing rings that were used here. There's one of the packing cases there. So they are designed for extremely high pressures, and lots of things matter in these things to prevent cracks and also fretting. Also within Burkhart, we produce what's called a Labyrinth compressor. So here again, we don't have any compression and rider rings. We use vortexes effectively to seal the piston. So the piston has effectively a screw cut thread in it. There is a rough cylinder liner. This is mainly to allow this to bed in correctly, and these vortexes seal the gas on the piston. And of course, these machines are very good for dirty gases. So if you have a dirty gas compressor, these things do work really well for that. Even in the packings, we use a labyrinth situation. So here we have quite a coarse labyrinth. We can also use a very fine labyrinth as well for them. Then if we move on to a compressor that I guess most of you are more familiar with, a horizontal compressor. So here we have a 5-stage one, and you're going to be seeing some pictures from this compressor later on as well. So we'll be discussing during this presentation the piston rings and the rider rings, main packings, and also the oil wipers as we move on through. A couple of examples here. So we have a high pressure packing case that we would use in one of our compressors, and also we would recommend in any other brand. We have what we call a heterogeneous design system. So for instance here, pressure breaker. Then we've got, in this case, some triple circle rings, which seal what we call the dynamic portion of the gas pressure, and then some radial tangent plus backup to seal this, what we call the static. And then you've got some side-loaded packings for the vent and the purge or the buffer. Double acting piston up here. I'm sure you've seen one of these scarf jointed rings before. Then it's probably designed for hydrogen, because we've got a lap jointed ring here to really try and seal the gas from going down the piston. And then of course the rider rings that we like to put in the center to prevent metal to metal contact. So just to explain a little bit how a compression ring works. So we have our cylinder liner, piston, the ring, gas comes along, pushes it to one side of the groove, comes round the inside and pushes it out onto the cylinder. And effectively they're the forces that enable this ring to seal. Then if we take the rider ring, so we have a rider ring here, its length is determined by the weight of the piston and half the weight of the rod. The ring axial clearance mentioned here is extremely important for rider rings, because if you think of the materials we're using can have up to 10 times the coefficient of thermal expansion of steel, we need to allow for that, because if this closes up in that groove, it then creates extrusion and we have problems. And then of course we have the piston cylinder clearance, which gives us our allowable wear. Packing rings, they operate in much the same way as a compression ring, piston ring. Gas comes along, up through the groove, round the outside of the ring, forcing the packing onto the rod and against the opposite face of the cup. You do get a little bit of leakage, but that we always get because these are a dynamic seal. The springs in reality are only there to enable the ring to be fitted. So in fact, if you take that first picture, that spring was doing nothing later on in the wear of that ring, but the ring was still staying there. but it's the same. Then if we think about the suction stroke, the reverse stroke, the gas comes back through that gap in the radial ring. We then get some re-expansion of that gas, which then gives us some cooling effect in the packing case, which is very good for the system and helps keep it all cool, promoting good ring life. Now, if things go wrong and for some reason the ring is fitted, this pair of rings is fitted in the wrong way, then that radial gap becomes a leakage path, and the gas just flows through that leakage path. And in fact, we encountered one packing case where all the rings were installed in the wrong direction, and rather than having 10 normal cubic meters per hour leakage rate, they were having 250 plus, and it could have been an awful lot more. It's just the size of the flow meter was 250 meters. But then the problem is on the suction stroke, the ring is then acting as a seal. It's sealing in the wrong direction. So we get high pressure gas staying here. We don't get the cooling effect from the gas re-expansion. So we end up with premature ring wear. So it's always very important to make sure the rings are installed in the correct direction. Many of you will have seen an R&T with a backup ring. So why do we have the backup ring? Well, there's kind of two reasons for it. The main one that most people are familiar with is the gap between the rod here and the inside of the cup. Filled PTFE ring can extrude down that at higher pressures and temperatures. So this anti-extrusion ring is there to prevent that. So we go from, say, 120 thou gap to a gap of 4 thou to 6 thou given by the anti-extrusion ring. But it also does another thing for us in the fact that it actually improves the sealing efficiency. So we will often use anti-extrusion rings to improve the sealing efficiency, even on lower pressure systems as well. And also in a cup of the same dimension, we end up with thinner rings, which means we generate less frictional heat, which is also good for the system. So some of the challenges we face. We mentioned surface finish in terms of that plunger. Well, it's also equally important for your piston compressor, particularly for dry running machines. I must admit it's still important for a lubricated machine, but in a dry running machine where you don't have the oil, the material has to effectively lubricate itself. So we start off with a particular surface finish, and that can be dependent on the material of the ring or the hardness of the counterface. So it fills gradually as it's wearing, it fills up the voids within the counterface, takes the top off, and then effectively it runs on itself. And it also, those worn off tops gives us a bearing surface. So once this film is laid down correctly, you can end up with a really good ring life. And in fact, the longest one I ever encountered was 10 years. Thankfully, as a ring manufacturer, there weren't too many of those. If we then move on to gas and or process, this is also an issue. I mean, if you take gases like ethylene and propylene, they can be prone to, for instance, polymerizing within the compressor if it's not being operated correctly. The temperatures are maybe a bit too high, and you can see some examples of this. So for instance, the valve is out of a propylene compressor that we have, and then this is out of a booster primary. So that's polymerized ethylene there as well. So you can see some of the challenges. And of course, if you get dirt and debris as well, it has an issue on the ring life. So keeping your gas clean. Cooling circuit, please don't forget your cooling circuits. I mean, you can see this, the example of this cooling circuit in a packing case. Are we getting any cooling in that packing case? And the answer has got to be no. And it is important because that cooling takes away the frictional heat that we generate in the packing case. And don't forget to make sure your cylinders are also clean from dirt and debris. because if you get a cylinder cooling circuit that's clogged as well, that will also have an effect on your ring lives. And again, moving on to dirt and debris, please don't take out your inlet filters. Here's an example of one that came through from what was supposedly a clean hydrogen machine. And I mean, this is a 10-year-old machine. And that piece of grit there, that's probably about 5 millimeters in size. So you can just imagine what happens if this gets through into your cylinders. Damage the cylinders, take out the valves, do all kinds of damage. So it's very important to make sure their systems are kept clean. And we come back to this compressor.
Okay, is that better?
That's better. Yes.
Right, sorry. So, sadly, I can't see what the comments are. I don't know, Andrew, are you able to relate any of the comments in respect to this picture?
Oh yeah, so let's see here. There wasn't nothing came in through the chat, but there, I guess through the questions, there was one comment about, basically it says, looks like new after 9 months, good material selection.
I would agree. I agree, and that's what I would say as well. But the other thing that really sticks out to me, apart from the fact there's no dry dust, there's no oil residue on there. And if you think the packing case is here, we've got the oil flinger, and there's the oil wiper. So the oil wiper has worked extremely well in this situation. This is a vertical compressor, and please don't think that oil wipers have an easier job of it in a vertical compressor, because they don't. It's just as hard. So these have worked really well in this situation, and we've therefore achieved a very good ring life. Here's an example where it has not worked so well. I mean, this one's even been cleaned up a little bit, but you can see here the mixture of wear, debris and oil. And of course, that wear, debris and oil in a dry running system will take down a dry running packing very quickly. You'll end up with a polished rod as well, so you have to refurbish the rod more as well. So don't forget these oil wipers. The other concern, of course, is any oil that has come out of the crankcase needs to be thrown away. So therefore, if you're not throwing the oil away, you're being more environmentally friendly. So that's also nice to the environment. Here is an example of a oil wiper that we would use. We typically start with what we call a pre-scraper. So we take most of the oil off the rod straight off the bat. Then we follow it up with some scraper rings. Admittedly, now we would put each one of these rings in its own cup with its own drainage system. And then we follow up with the side-loaded packing. And this side-loaded packing is not about preventing gas going into the crankcase. It's about preventing oil mist going into the distance piece. Because if you get oil mist in the distance piece, it will go around the oil flinger and still contaminate your packings. So as I say, please don't forget your oil wipers. Here's some of the horrible gunk that can be generated when there's too much oil, too much wear debris. And also, actually, even though this is a lubricated machine, this includes cylinder wear as well. So it can happen even on a lubricated if things are not right for one reason or another. As part of developing our own materials, we set up our own plastics laboratory. And in this laboratory, we can determine all the properties of the materials that we develop. Specifically, if you like, the coefficient of thermal expansion, which is very important when we come to design things. The creep, so we know what pressure we can use a ring to, and to make sure that a ring is flexible enough that you can install it correctly. Not only can we analyze our own materials, make sure that we're doing things right. If we encounter a problem in the field with somebody else's material, we can also analyze that as well and determine maybe what's going on. Has it been sintered properly, that kind of thing. So we can do that, and that is also a service that we can offer. So to do that, I always liken a good material to an espresso. You could have only potentially 2 ingredients in that cup of espresso, water and coffee. And if you don't have a good coffee, if you don't process it correctly, you end up with a bitter cup of espresso. So processing and ingredients are vital to achieving a good, reliable ring material. So we're always keeping an eye out for the newest polymers that are available that maybe can offer us something better than what we already have in some of the challenging gas applications. I mean, during the chat before the presentation started, we were discussing hydrogen. Hydrogen pressures are going up 500, 900 bar to achieve what you do. So we need materials to achieve that, and that's part of what we're working for. Optimizing the fillers to match the polymer that we're using. So the watt, the size, and the shape, both of those matter for mixing the materials in a homogeneous fashion. And of course, getting the percentages right. I mean, in North America, quite often you refer to a carbon and graphite filled PTFE as CFT, carbon filled Teflon. Well, in reality, it's not. It's got a little bit of graphite in. And that graphite is actually very important to making that material a much better grade. Controlling the processing, the mixing, making sure we've got it all mixed and you don't see those little white specks that you sometimes see in materials. Compacting, whether it be cold or hot pressing. And of course the sintering. It's just like baking a cake. Stick it in the oven, run it through a cycle, and away we go. And these are all important things that we need to make sure we keep controlled so as we produce a good material. You could ask why we add fillers to, say, a polymer material. We'll take PTFE in this case. Well, it improves the properties. So, for instance, the resistance to creep, so we can use it at higher pressures. Wear resistance. PTFE on its own has a rubbish wear resistance. We improve the thermal expansion so it doesn't grow so much. So that means our end gaps on our rings can be that much smaller. Thermal conductivity is also improved, though it's still, you have to consider that all our ring materials effectively are thermal insulators. But if we take then some of the properties that we care about, like expansion, wear, tensile, and creep, and then we compare those properties, say, to filler content. So carbon, so we have, for instance, here 40% filler, so 60% PTFE and 40% filler. Then if we take the y-axis having whatever factor is needed, so whether it be expansion or wear in the case of the red graph, and then we lay those over one another, we can kind of think to ourselves, where do we want our material to be that gets the best from those properties? And so you kind of guess somewhere around the 35%, which is not bad. There are quite a few grades out there that are about 35% because it offers good range of properties, good creep, good wear. You can install it around a piston without breaking it, etc. If we also look at expansion in particular, you can see we have 2 lines for expansion. And we have 2 coefficients of thermal expansion for the same filler. That's because you need 2 different types of PTFE to get the extra filler in. But because we're using a different PTFE, we end up with a different property. So it just highlights the importance of the ingredients that you use to achieve a good material. So we have, from all that, we have our own range of materials. So for instance, here we have a carbon and graphite filled PTFE. This particular one is developed for lubricated duties. We also have a couple of others that we can use for dry running applications. If you remember the pre-scraper in the oil wiper, that tan material, that's the polyimide filled PTFE, and that we use for oil wipers a lot. It's quite soft, it conforms to the rod. The rod changes temperature during operation, So this is able to cope with that slight change in size, because it doesn't take much of a gap in an oil wiper to get an oil leak. We have another material here, which is also a carbon and graphite filled PTFE. Actually, it's got two types of PTFE in it. This has better physical properties than, say, the Persisto 79. So therefore, we can use it at higher pressures and temperatures, which means we can use a more cost-effective material before we, say, move up to a peak material. Persisto 850, because an awful lot of our applications are hydrogen-based, this material was developed for hydrogen, and certainly so far we found it to work really well, and it's based on a PPS material, and it has a nice red tinge to it, so you'll see a slightly better shot of that later on as we go. And because the 850 gave us hot pressing within our process portfolio, we are now able to produce our own peak materials. So we have developed what we call Persisto 8400. We believe it to be less abrasive than some of the other peak materials on the market. So we use it in some of our, certainly in some of our higher pressure lubricated applications, some of the dry running ones as well. And also it gets used in the Labyrinth compressors as a Labyrinth packing. Also, we have more materials in this family, and we are continuously developing. So hopefully I will get to present those to you at a later webinar. We also have some test compressors available to us. So if we take, for instance, this hydrogen compressor, at the moment he goes up to 200 bar. We're looking to increase that. So before we go anywhere near one of your compressors, we can test our new materials, our new ring designs in here and give them a pretty thorough testing before they come anywhere near to one of your compressors.
Hi, David, we're at the half-hour mark here.
Okay. Right, so what was the answer to the poll?
Would you like me to share the results now?
Yeah, go.
Okay.
Go for it. Let's see what people said.
So most people said wrong. Yeah, go ahead, David. You go ahead.
Sorry, what did people say?
Oh, can you see the results?
No.
Oh, interesting. Okay, so 35% said assembled wrongly, 31% said the wrong material selection, 19% said dirty gas, and tied at 8% each said incorrect surface finish and not reading the manual.
Yeah. Well, certainly not reading the manual is one of the main reasons, I would say. And of course, because the person hasn't read the manual, they got assembled wrongly. If we move into the next picture, we can add a little more detail to this one, and you can see why. So this is actually the ring set before that ring. So this is the first cup after the cylinder. And I don't know if you've noticed here, we have a double tangent. This is a double acting sealing ring. So it's working in both directions. You would not normally put such a ring that close to the compression chamber. You just don't want to seal that early on. So that is part of the problem here. So the gas has got in behind. These rings have kept it there. We've not had any cooling. And this ring has just taken the whole brunt of it. Oh, sorry. And then if we moved on to the next one, which is the picture I showed you, the same thing has happened. This ring has just done all the work. And I have to be honest, I'm surprised this guy hasn't copped it more, but it's simply we have the wrong ring design in the wrong place. Then if we go on here, we have a radial tangent. It's pictured as it should be actually, but I have a feeling it was actually installed incorrectly based on that line. So that's okay, maybe. Then we have a radial tangent installed in the wrong direction. And you can see here, so the gas is just going to flow past here and do nothing. And the same applies here. And then in the last one, again, radial tangent. This one suggests that it's been installed correctly. So yes, they were installed wrong, but if they'd read the manual, you can quite clearly see radial ring, tangent ring, anti-extrusion ring. And it doesn't matter whether it's a Burkhart manual or another's manual. This information will be there. And if ever in doubt, please either consult the manual or your ring supplier if you choose to use somebody else. Preferably, obviously, I'd like you to use us. So yeah, consult the manual. The information is there and it can prevent heartache. As I refer back to the compressor where they leaked hydrogen for 5,000 hours before they had the opportunity to change out. They lost a lot of hydrogen because of that mistake. So coming back to how we can analyze rings. So for instance, here are some rings that were analyzed after 4,000 hours of operation. They didn't work as well as we'd like. And you can see here we found some iron oxide, we've got some silicon oxide, some aluminium oxides, and all these parts have got embedded into the ring. And this is actually a lubricated compressor. By analyzing what's there on the surface of the ring, we can determine where some of these things have come from. So the silicon oxide and the aluminium oxide has likely come from the PSA unit in front of the compressor. And that will probably be because the filter is not a small enough size. Then the iron oxide, possibly apart from the cylinder liner, it could even be piping. All not good for ring life. Also, as part of this exercise, we did a detailed measurement of the cylinder. So if we take a vertical axis down this compressor, and if you think of rolling it round the axis, you will effectively have the cylinder. And then this is then laid out flat. So you can see here the wear that you get where the compression rings are, both here and here. And if you refer to, for instance, API 618, it says when you calculate a rider ring length, you do it over 120 degrees. Well, this proves that that's the right number to use because this is 120 degrees where the rider ring has actually worn. So these again are things that we can do to analyze what's gone on and potentially what's gone wrong in a cylinder. As part of to improve ring lives and efficiency as well, we have several rings that are peculiar to Burkhart. So one is what we call the PJ ring. We developed in-house. This particular one has a pressure balance design. So we have the groove on the outside and the hole through. It's very good for, say, hydrogen. We can also use it dry running and lubricated, and it maintains its sealing efficiency throughout its life, which if you take, for instance, a conventional scarf jointed ring, the gap just gets bigger and bigger. So it gradually just lets more and more gas through. So this helps prevent that. And if we take an example here, you can see a picture of a worn one, and it's actually off that compressor I showed earlier, that horizontal compressor. Dry hydrogen, it's got a few other bits and pieces in, non-lube. We got 27,000 hours out of it. And I reckon that's actually pretty good for a non-lube hydrogen machine. If we then move on to the packings, we have what we call a multi-piece ring. And this is now my new favorite ring of all time. There used to be one called the Roger ring, which is very similar to what you would call a PBU in Americas. It keeps its sealing efficiency throughout life. It's very good for oxygen service for anybody who's got an oxygen compressor because it has a very small contact area, so we don't generate much heat, which is very important with oxygen. And if something does go wrong, the dividers that keep the segment in place also keep that spring off the rod. So then the spring doesn't cause secondary damage. And I go back to those earlier pictures where you saw the spring nearly there. It's very close to that spring coming loose and potentially causing more damage. So this won't happen with that. And because of this these posts, then the whole ring then stays in the correct orientation as well, so it doesn't cause a problem. And it still continues to do a little bit of work until you're able to service the compressor. And here we have some examples of worn rings. So the white rings here, these were used in oxygen. Previous to these rings, they were getting 4,000 hours life. These rings achieved 6,000. And actually, they could probably have gone 18,000 hours. And this is 25% glass fill material. So it's not the best oxygen material out there, but these rings gave very good life. This ring here on the right is actually from Canada. Ask yourselves the question, how long do you think this ring has worn? Been running for? And the answer is 8,000 hours. And apart from a few marks here, you could stick that thing straight back in and it'll run another 8,000 and longer. This MP ring has again come out of that compressor you saw earlier. So this packing ring has done 27,000 hours. And you can see in comparison to the new ring, it's still got a lot to go. So this is one of the reasons why I love this ring. Apart from the fact that if trouble happens, it won't cause any problem and it'll still do some work. It just gives a very good ring life. So that's the end of my portion of the presentation. So I'd like to hand back to April, who will give you some closing words. So thank you for listening.
Okay, thank you, David. It's actually funny. It kind of popped in my head there while you were showing the multi-piece rings. I've got the Burkhart demo kit here at home, and because I'm still fairly new to Burkhart and still learning myself, I was playing with the pieces, and my son, I'm sure he's going to end up being a heavy-duty mechanic or a millwright himself. So this stuff really interests him. And he took one of those apart and thought he had broken it and that it was the end of the world. And they're pretty cool rings. And yeah, I had to reassure him it was okay, and we put it back together. And then he thought it was even cooler. So so yeah, thank you everybody again for your attendance today for our technical presentation. We hope that we have achieved our goal of educating you on dry running sealing materials and reciprocating compressors. We are a global compressor OEM with over 175 years of experience. We have a location in Edmonton that covers a broad range of services for compressor component repair. And we do offer shop tours to anyone that is interested. So if you'd like to see our setup there in Edmonton, please feel free to contact me. I'd be more than happy to set that up for you. Our Canadian locations are in Mississauga, Ontario, Edmonton and Drumheller, Alberta. And our areas of expertise include field service, valve service, spare parts, engineering, technical support, revamps, training, and condition monitoring. And as I mentioned in our introduction, we service all brands of reciprocating compressors, so please reach out to us for any of your compression needs. And we're going to finish off the presentation with questions and answers now, which I will pass on to David and Craig for anything technical. Thank you.
I just want to make one quick point to this. The compressor population is only Burkhart machines. CSM services and looks after hundreds of compressors in that area. So
yes, thank you, David.
Yeah. So, all right, let's move on. Okay.
Ralph, did you want to field the questions, or do you want me to answer or read them out? All right, you're still on mute.
Oh. Right. Andrew, can you go ahead with those questions?
Sure. So the first one here was whether you use a seal gas to achieve zero leakage.
You can do. I mean, you can design the packing case to have a nitrogen buffer in there. Yeah, buffer. But in truth, it's still about controlling the gas and where the leakage goes as much as anything. There are ring designs that you can use that can really improve the amount of leak gas that you achieve, or you don't then, or should I say you don't then get. So as I take, we've got one hydrogen compressor, which is 6 cylinders, 100 bar discharge, and it gets 10 normal cubic meters per hour, which across 6 cylinders at 100 bar isn't bad. And we've got some other good examples of similar low leakage rates as well. So it's about ring design as much as anything.
Okay, thank you.
The main idea is about stopping the pressure before you start the sealing. So you step down the pressure through pressure breakers, and then the sealing elements can do their job of actually sealing. So that's the philosophy.
Excellent. So I guess another question would be, what kind of mean time between failures would you expect? But I guess that really depends on your circumstances.
It does. I mean, you take oxygen, for instance, a year, some materials and some situations you get longer. Hydrogen, we showed you in a case where we've got 27,000 hours. There's another compressor where we've offered 16,000 hours warranty. If you move on to nitrogen, provided you use the right material, you can go up a year, 2 years. But then if you've got dirt and debris in the gas, or you haven't maintained the compressor correctly, you haven't maintained the packings properly, then obviously that has an impact on ring life.
Okay.
Yeah, just want to say we have a few more questions, but we still have time, 15 minutes or so. So please send questions.
Mm-hmm. So I'll keep going here. So there's a question here. I'll see if I can interpret this properly. The meaning of dry gas seals is lubricating by nitrogen or never using any lubes. So I guess, I don't know if you can interpret that properly.
Sorry, can you say that again?
I think it's pertaining to using dry gas seal systems and whether the nitrogen.
We're not using. Are we talking a rotating seal as opposed to one for a compressor?
A RECIP, yeah.
Because a dry gas seal is typically a carbon. I would say is a carbon seal for a rotating application.
Yeah.
Rather than the reciprocating application, using it in that way. But I mean, you have, again, within a RECIP, you use nitrogen in the packing to help buffer and protect any hazardous gas getting through to the atmosphere or even into the crankcase where it can cause damage.
In some ethylene services, you can use ethylene, like sweet ethylene or even natural gas as well as a gas. It really will be designed for that application to ensure that you have the best setup to make sure that you're keeping the gas in the cylinder side, in the working side, and that you're keeping the crankcase side safe.
Yeah.
Yeah. So they use the acronym DGS. I was assuming that meant dry gas seal, unless it means something else.
Not to me.
Dry gas seal, yeah.
Okay. Here's another question here about whether you can switch lubrication from a non-sealed system or switch to lubricant from a non-lube.
Yes, you can.
You can go both ways, yes.
Okay.
Yeah, I mean, it's more difficult to go from lube to non-lube because there's often some physical constraints of the compressor. I mean, like making sure, for instance, that no portion of the rod goes through the oil wiper, then goes through the main packing. Your rider ring length needs to change as well. You need longer rider rings. So there are some other things, and of course you've got to make sure you clean your pipes out because a little bit of oil and a little bit of wear debris, it's gone to rats. Sorry.
So I've actually sent the questions to you. I don't know if you could read them or not, David. You can go to the questions and expand that out.
All right, okay, let's have a look.
So there's another question about, and I guess this would be more for Craig, what API standard refers to the overhauling of a horizontal compressor?
The API 618 would probably cover most of the design and even have some specifications for how how long things are expected to last for horizontal units or the 11P. But it's hard to put a certain specification on a compressor because the same frame may run 400 RPM, may run 750 RPM, may run 900 RPM. So the wear rates will vary depending on the gas, the speed. There's too many variables in there to say this specification goes with this. You could get guidelines. If you don't have guidelines, you can reach out to us and we can talk about your situation. But most compressor OEMs will give you a guideline, and your specific unit will be kind of based on your experience. And if you're looking to extend that, that's when you could come to somebody like Burkhart. We could look at your situation and we could maybe offer suggestions to improve that.
Okay, so here's another question. This one again is specifically for Alberta. So coming forward in Alberta in 2021, there's a directive D60 which is going to be implemented. So I'm not sure if you're aware of that.
That's the fugitive emissions.
Yeah.
Okay. So they said there's a limitation of 0.35 cubic meters per hour per throw. So do we have an average leakage rate that's able to be obtained using the MP compression rings?
I would have to say no, specifically, but that 0.35 is similar to what you would use for your nitrogen feed as well. That would be the rate that you would feed the nitrogen into your packing case.
Yeah.
So it's kind of matching that. And again, it's going to be for probably mostly for methane, I guess.
Yeah, that will be mostly for the methane emissions reductions. We were consulted a little bit on that development of that standard. We were just consulted. We didn't have much say in it, but yeah, there definitely is better solutions than what's out there on the market right now.
Yeah.
But a lot of it also depends on, as David mentioned earlier, the counter surface, what we call the counter surface finishes. So your rod finish, your liner finish, the types of material you're using, those all have to be correct to obtain even your rod straightness. If you have a bent rod, it will not help your sealing at all. So it really depends on the physical shape of your compressor as well. That in combination with a good setup of rings and riders, you'll have very, very good efficiency. We recently overhauled a machine in central Alberta, redid the cylinders on it and redid some rings and packings on it, and they ended up getting approximately 25% efficiency increase in the gas flow coming out of it, and that was on a midstream booster station. So you put the right materials in, you got the right sizes, you'll be impressed with what your compressor can actually do.
25% is incredible.
Yeah, they were putting OEM rings into a cylinder that was not round anymore. So we were just getting blow-by over the rings. Wow. So once we made the cylinder round again, redid the surface to the correct surface finish, put the proper oversized rings in to fit, closed up all the gaps, it was, 25%. Let's just say that overhaul paid for itself in about a month.
Yeah, that's just proper attention to detail.
Oh, yeah.
You should be simple, you know what you're doing, I guess. Okay, so when you've got condensates in your gas, how would you address that to increase your mean time between failures?
Getting the condensates? Oh, I'd rather you got rid of the condensates. At the end of the day, if you get liquids in the gas, it's trouble. Your only real option is to start considering using harder materials. So you're potentially looking at using a peak rather than a filled PTFE, something that's not going to get bashed around quite so much.
The condensates in gas, I always try to remind people we're compressors, not pumps. So pumps are for liquids, compressors are for gas, but it is inevitable with condensates, and there are, especially in Alberta, there's some really good technologies for knockouts in between stages. But with the ambient temperature in Alberta from -50 to +30, all year round, it makes it a challenge, that's for sure.
Yeah.
So tell us what kind of condition monitoring, or actually no, performance monitoring is the question, not condition. Performance monitoring, do you have anything that you use?
The leakage, the flow meters seem to be the new trend in industry. They're not just taking packing temperature anymore. So traditionally there would be an RTD mounted in the flange cup, and you would just, once you started seeing that RTD trend up, you knew you were getting blow by past your packings, and then you knew it was time to start planning a change. Now, especially with this new regulation in Alberta, it's focusing more on flow, and you can actually quantify the flow with a flow meter. So that seems to be a very good trend. There's also rod drop in horizontal machines. You can measure your rod drop. As Dave mentioned, rider bands are very critical. Particularly in a Burkhart design, we tried to keep the rider bands on the center of the piston, because the rider band should not be performing any sealing activity. They're really there as guides. So if you've seen that picture, that colorful picture where Dave was showing the wear in the cylinder, that 120 degrees in the middle, there was no wear. That's because that's where the rider bands are guiding the cylinder. So that would prevent rod drop, and by rod drop, that would be the piston running back and forth and getting closer to the cylinder where it could actually make metal on metal contact. And as the rings wear on the bottom, the gas will blow by over the top. So condition monitoring, rod drop, gas flow, even temperature is still a good method, and overall flow of your compressor. If you're measuring the overall flow of your compressor, if it starts to tail off, then you know that gas is going somewhere.
Yeah, or just recirculating within the cylinder.
Yeah, and that creates heat and wear.
Yeah.
So Brandon Graff's got some questions here, related to rod drop sensors, and I've unmuted him. So if he wants to, perhaps you can unmute yourself and ask more specifically yourself.
Yeah, hi, Craig and David. I guess we've explored installing the rod drops on there. Have you seen any cases where it's been of benefit? I mean, it's quite a extensive setup to put them on some of the legacy equipment within Alberta, the cost behind it. So it's going to be whether it's worth it or not.
Yeah, it is a difficult one. It's such a nice thing to have, but just to install 2 rod drop sensors, you're probably into it for under $50,000 to $100,000 by the time you've wired it all in. Then you got to get into the distance piece. You got to make the sensor bracket, and then you also have to consider is your piston rod tungsten coated? Is it not tungsten coated? There's a lot to consider there. Really, at that point, if you wanted to get ahead of that, really temperature monitoring and flow monitoring are really your next 2 lines of defense.
Yeah.
Does that help?
Rod drops diff.
Yeah, thanks, Craig. And that's why I guess what we've always been doing is the temperature and flow. And if we do see any difference, and we know we got rings starting to go or packing starting to go, but just looking at the cost, it's nice to have, but to justify the cost has been pretty hard.
Yeah.
I think if you really want to start pushing the system to really maximize your run times, then you've definitely got to have a rod dropper in there.
Yeah.
And of course, it's not an easy thing to monitor anyway. It's what they do with the information to get you a reliable distance is quite difficult. So,
especially on the higher speed units, it can be quite difficult. And there's your piston rod condition is very critical. You can't have any bent rods or anything like that.
Oh, absolutely not.
But it's amazing what a rod drop can tell you. You can even indicate you're starting to fail valves due to thermal expansion. It's amazing what a rod drop can tell you.
Yeah.
Okay, and then so we have a question just in general about the relationship between Burkhart and CSM. So you can just explain that a bit.
So Burkhart was looking to start our own workshop here in Edmonton years ago, and CSM came up for sale. Burkhart purchased CSM in 2017. At that point, it was start a brand new shop from scratch or buy 3.5 decades of experience. It was a pretty easy decision. They're really great people at CSM. So we needed a workshop to bring our equipment for repair, our customers' equipment for repair locally in Edmonton. So it's been a great teamwork there, and we're looking to expand, obviously. CSM, what's funny is CSM did no Burkhart work, and they were working on all non-Burkhart equipment. So it's been a really good relationship so far.
Super. Okay, well, that wraps up our hour. Any other final closing words?
No, thank you very much for everybody's time. Please look us up on LinkedIn or on Google. We're all over the world. We have 50 service centers globally, so we're somewhere close to you. And we're really focused on making your compressors run better and longer.
All right. So there'll be some follow-up questions we'll put in LinkedIn as well, so we can always carry on from there. Okay, thanks everybody. We'll see you again in March.
Thank you everybody for listening.
Thanks, Rob. Thanks, Ryan.